All right. This will be the last in a little set of videos looking at the first uses of how gradient works. In our book, this would be sort of the last little trick you need to know in section 13.7. So, if we were to take this function as it's written and calculate its gradient, this is going to give you a two-dimensional calculation. All right, the problem with a two-dimensional calculation, it only gives you a vector in the xy plane. It doesn't give you the third dimension. What we want is this normal vector in 3 dimensions. And it does make a surface if we could graph this. And so the question is how do we go about generating that information? Well, the answer lies in the meaning of f of xy, and one of its alternate notations is simply to call it z equals, and then z would equal then x squared plus 4xy minus y squared. Please remember, we don't actually know what this graph looks like, but we know it's a three-dimensional surface of some kind. I like to think if you took the sheet off of your bed and just held on 2 hands and just waved it up and down really fast, the graph would look something like that maybe. So, if we were to slide this over, x squared plus 4xy minus y squared minus z equal to 0, then this now has 3 variables in it. And we're going to relabel this g of xyz equals x squared plus 4x, xy minus y squared minus z, and it equals a constant. Now, because it has 3 variables, if I calculate the gradient, remember the gradient being a vector, where the first term is the x partial derivative, which would be 2x plus, that's right, 4y. And the y partial derivative would be 0, 4x minus 2y. And the z partial derivative is just negative 1. That's the only term with a z in it. This will be a normal vector to the 3-dimensional surface that we see right here. Now, let's just get some coordinates to play with. So if we started the problem over again, but I provided you coordinates and we were curious, hey, what's going on this graph here at the point where x is 3 and y is 1, we could substitute x is 3 and y is 1, and you will get 3 squared is 9, 4 times 3 times 1 is 12, minus 1 squared is minus 1, you're going to get 20. So we have a point on the surface at 3, 1, 20. There's our coordinates. So, I come back up here again. Here is your task. Can you write the equation of the tangent plane? Can you also write the equations of the line that is normal to the surface? Parametric equations of the normal line. I think you will find that I skipped one setup step, but I will post the solution to this into Canvas. Good luck.